So I'll continue with torsional theory. And as we discussed, I'm talking about the torque now, right? So I covered minus y tau zx first. And now I'll talk about the next term, which is x times tau zy. And that's positive, and that contributes to that moment. So the integral then gives you the moment, the total moment due to the shear stresses acting on the surface. So what is the next step then? Is that, and I'll then substitute into each of these tiles what this in terms of Prandtl stress function. I already showed you what tau is in terms of Prandtl stress function, and you can see that I have it here. I provided the formulas for Prandtl stress function. All you have to do is plug that in to the torque equation, and then when you do that, you get this formula. Now, what you can do is a little trick that's done in a more advanced course, but you can actually do it yourself if you know calculus, and you can get dangerous with it. You can integrate these equations by parts. And when you integrate these equations by parts, after you do some math, you get this plus the boundary term that's a contour around the circumference. So around this body of material, I can do this integral. It's going to show up when I integrate this by parts. And that integration by parts, when you do that, you'll notice that phi shows up alone. And what was phi around the circumference? 0, because of Cauchy's relationship. So this goes away, completely goes away. What is the derivative of y respect to y? 1. So you get a phi there. What is the derivative of x respect to x? 1. So you get 2 phis instead now. So that goes away because phi is 0 at the boundary of that. And so what I get now is that m equals twice the integral twice phi times dA. Phi, remember, phi is a Prandtl stress function. So let me show you the step-by-step on actually how to use these equations. Because what I showed you so far is the derivations of these equations. But in your mind is, how do I actually use this? So let me show you how this is used so you can understand how it's used and you can apply it. So step number 1, you choose a function phi such that is 0 around the boundaries of the problem you're trying to study. So I'll show you an example later on. Then after you choose a function phi, then you plug it into this equation here. It's not the biharmonic equation, that's an error of mine. Here, alpha is the angle of twist, g is the shear modulus, and phi is the Prandtl stress function for which you made the assumption in the first place, which has to be phi equals 0 at the boundary of that structure you're studying. You then take this equation, solve for phi in terms of alpha, and I'll show you an example on how to do that. Once you get phi, you plug into the moment equation, and then you can get the moment in terms of alpha. And now that's very powerful, because now if you apply torque, you know how much the structure will twist, because that gives you that formula. It tells you how much it's going to twist. Not only that, once you know this, you can actually calculate the torsional constant, J. So it tells you, and this is a moment, the polar moment of inertia, in fact. You can actually find what that is as well for that cross section. So not only this approach gives you what the relationship between the torque applied is and how much that body of material will twist, but also it tells you what the polar moment of inertia is for that body. Step number 6, now that you know phi, and you know phi from this equation here, you can then calculate what the stresses are, the shear stresses are. And once you know the shear stresses, you can get the warping function kappa that I had discussed earlier. Very, very cool. Let's why we don't step into an example application.